Hello, my name is Juan López Muro. I am a PhD student at Rutgers University. Our project is called Control Co-Design Optimization Framework with Mixed Fidelity, Fluid and Structure Analysis. As a part of this project, my presentation focuses on the development of representative reduced order models and control tools for offshore floating wind turbines. The aim of our research is to develop a computationally efficient optimization framework for design of floating offshore wind turbines. Our specific aim is to utilize high-fidelity aerostructural tools and to derive reduced order models directly from these high-fidelity tools. Our project is executed by a multidisciplinary team consisting of Rutgers University, University of Michigan, Brigham Young University, and NREL as primary partners. We are also collaborating with the National Technical University of Norway and the Technical University of Denmark. Traditional wind turbine designs frequently rely on the design and optimization of each subsystem in an independent manner. This is often referred to as a sequential design approach. Today's floating offshore wind turbines are highly coupled systems of electrical grid, power electronics, and different structures and mechanisms interacting in a dynamic fashion with the surrounding air, water, and soil. In this project, we consider a control co-design approach, taking into account the interaction between the subsystems and applying control concepts in the design process with the aim of obtaining a more optimal solution. Traditional wind turbine controllers are based on simple 1 degree of freedom models. Therefore, the mechanical fatigue or equivalent damage load is not taken into account in the controller's design phase, but it is only computed a posteriori. This presentation introduces the modeling method to derive a control-oriented reduced order model and a particular control strategy for floating offshore wind turbines in the context of the first phase of our Atlantis project. During this short presentation, I will first introduce the reduced order modeling module and explain how we can get a representative model of a floating offshore wind turbine that can be used to design the control system. Next, I will introduce the Control and Reference Governor module. I will briefly describe the state of the art of wind turbine controllers, and then I will introduce our novel approach, which consists of two main ingredients: H-infinity controllers and reference governors. After that, I will show some results and discuss the benefits of our approach. Finally, I will talk about the ongoing and future work in our Phase 1 ARPA-E project. Traditional wind turbine controller design is based on a simple dynamic model where only the speed of the generator is of interest. Therefore, a first-order model like the one displayed here is sufficient. This is the case of the legacy wind turbine controllers and the recently proposed Roscoe controller currently being tested on a small-scale wind turbine at the University of Maine. As exemplified in the motion picture on the right, innovative concepts of floating wind turbines tend to have very long and flexible blades and in general slender and flexible structure. In our approach, we aim to make the wind turbine extract the desired wind energy while reducing as much as possible the mechanical fatigue of the structure. To do so, we consider a multi-degree of freedom model to capture the dynamical behavior of the main structural components of the system. Here, I introduce the reduced order model to be used through the controller synthesis. We can see an illustration of the model in the figure on the right. This model aims to capture the dynamical behavior of the main structural components of the system, namely the floating platform and the dynamic vibration absorbers, the tower and the nacelle, the drivetrain and main rotor, and their interaction with the surrounding air, water, and soil. The equations of motion are derived using Euler-Lagrange mechanics, assuming interconnected mass spring damper elements. Euler-Lagrange equations are written in terms of kinetic energy and both conservative and non-conservative generalized forces. The contribution of conservative forces are related to the potential energy of the system, while the contribution of non-conservative sources are related to aerodynamic and hydrodynamic effects, damping mechanisms, and forces made by the actuators. The aerodynamic coefficients of the rotor blades are assumed to be a function of both the pitch angle and the tip-speed ratio of the blade. The parameters and coefficients that fit the reducer of the model come from other sub-modules. Actuator dynamics and nonlinearities such as magnitude and rate saturations are also considered in the modeling process. Each degree of freedom of the presented model can be enabled or disabled to analyze a specific set of degrees of freedom of interest. For example, the platform degrees of freedoms can be disabled to study the model of a fixed base wind turbine. Although the derived reducer of the model is intrinsically nonlinear, it can be linearized about an operating point to proceed with the design of the control system. The control system is responsible for driving the blade pitch, nacelle yaw, generator torque, and platform actuators, aiming to maximize the power coefficient while mitigating extreme loads on the structure. As already mentioned, our controller is based on two ingredients. First, we work with a synthesis of structured H-infinity controllers. They are designed not only to make the generator speed track a desired reference, but also to reduce mechanical fatigue. Next, we add reference governors to the closed-loop system to deal with system nonlinearities and address constraints given by the system design specifications. When formulating the control problem, we assume the configuration shown in the figure on the right, which represents the closed-loop system. P is a floating offshore wind turbine model, and K is a controller which uses the output measurement Y as inputs. The outputs of the controller block are the control signals and are applied to the wind turbine. The H-infinity method consists of minimizing the infinity norm of the closed-loop transfer between the inputs W and outputs Z. In other words, we seek to minimize the impact that the wind speed variations, the wave perturbations, and changes in the desired generator speed have on the generator speed tracking error, but also on the vibrations of the tower and blades. The tuning of this controller is based on some recent developments that are now extensively used in aerospace applications. This method allows us to choose the structure of the controllers. Linear controllers, like the traditional wind turbine controllers or the proposed H-infinity controller, they do not consider actuator magnitude and rate saturations, neither some other system limitations. It is well known that actuator saturations can destabilize a control system. So, after the controller design is done, we can focus on the reference governor design. Reference governors are add-on schemes for dealing with constrained systems. Here, they are used to keep some variables or control inputs within their limits and are only active when these limits are prone to be violated. They can be used to address blade pitch actuator rate saturations, platform actuator maximum allowable stroke saturations, generator speed tracking error constraints, or actuator power consumption limitations. Reference governor can be combined with any pre-stabilizing controller because they only modify the reference to be tracked by the closed-loop system when this one is about to violate some constraints, keeping the control system stable. Now, I want to illustrate the outcome of the reduced ODE model-based control system design through some results. In general, a floating platform can be stabilized thanks to passive or active systems. The active systems involve the use of actuators. In particular, I would like to show the improvement we can achieve when designing a platform controller aiming to alleviate tower loads. As can be seen in the figure on the left, the design of H-infinity controllers can contribute to damp the vibrations of the tower, mitigating its structural fatigue. The dynamic vibration absorbers located in the platform have physical limitations, such as maximum allowable actuator stroke, among various other limitations. Reference governors are designed to address this saturation and bound the stroke of the actuator within certain limits. The figure in the right illustrates the behavior of the translation of the dynamic vibration absorber mass when the floating platform is disturbed with a step hydrodynamic moment. We can zoom in to inspect the saturation when no reference governor is added. This saturation can persist in time for several seconds, degrading the performance of the controller. By the effective use of reference governors, this saturation can be avoided, reducing to a minimum the amount of time that the actuator operates at its extreme values and helping to mitigate structural loads. It is worth mentioning that these closed-loop results were achieved without losing generator speed tracking performance, and therefore extracting the same amount of wind energy. So far, we have demonstrated that our robust controllers can reduce the mechanical fatigue while extracting the same amount of wind energy. These structured control methods also allow to use more measurements inputs and enable smooth transitions between the operating points. We have worked on blade pitch controllers, torque controllers, and platform controllers. In the near future, we will also design the control system with the MIMO approach in all the regions of operation. In the future, we would like to implement our control strategies on the small-scale wind turbine of the University of Maine. OpenTurbineCoDe is meant to become open source and should be released in 2022. Before closing, we would like to thank Professor Mario Garcia Sanz for the opportunity to participate in the Atlantis program. Special thanks to Dr. Dylan Temple, Dr. Carlos Noyes, Madeleine de Freitas, Michael Olsen, and the entire Atlantis team for their support. For questions related to this presentation, please use the contact shown. For questions related to the overall project and our technology to market activities, please contact the PI at the address shown. Thank you for attending my talk, and please check out the other technical presentations in our booth.